Our volleyball team, which, by the way, last year had its best season ever on record, and the same coaches are here, maybe close to half of the same players, and they got a new bunch of recruits. But they're having a match tomorrow, September 24th, versus Coastal Alabama East, whatever that means. And it's on the Birmingham West campus at 5 o'clock. So if you can get over there and watch the match, they're really good, really worth watching. Okay? College Scholars Bowl is the team is recruiting players with knowledge of any subject matter, including history, literature, science, music, current events, mythology, mathematics, anything. Mr. West is the coach. His office is just down the half flight of stairs here. Go down the rooms. The office in between 259 and 261. That's his office. Talk with him there. He'd love to talk with you. Today is the last day for the exhibit, Darkness into Life, Alabama Holocaust Survivors through Photography and Art. It's been at the Birmingham West campus, the campus library there, since September 4th. Today's the last day. It looks like a really, really fine exhibit. Go by and see it if you have a chance. And the NASA Community College Aerospace Scholars Program is recruiting and receiving applications through October 16th. So a little over 3 weeks. So right around that to get those done. Okay. I haven't marked the roll yet. All 3 of you are here, which is great to see. Now, where we left off before, we're in Chapter 2, First Order Differential Equations, 2.2 Separable Equations, which are the most fun, I think, to do, generally pretty straightforward to do. And we're on Example 5 on page 51. Okay, and here's what it is. Solve this problem. Oh, remember last thing we talked about was integral defined functions. Functions when you can't take the integral, define it with the integral. Hint, this is one of those. dy dx is equal to e to the minus x squared with an initial condition y of 3 is equal to 5. All right. Now, how would you begin a problem like that? Write it in differential form, meaning you keep the dy by itself on this side and put all the things with x's on the other side, e to the minus x squared dx. What our typical rule after that would be then to integrate both sides, right? Left-hand side, even I can do. That's just going to be y. Okay? Right-hand side, no way. Substitution or anything else are you going to solve that integral directly. How do they say it? Explicitly. No way to do it. Not even implicitly. No way to do it. So basically, you leave it in that functional form there. Now, I jumped the gun on something here. Because you can't solve the left-hand side, you have to be more careful on the right-hand side. Okay, before, if you could solve the left-hand side, take an integral of that, you keep all your c's together. This one you can't do this way. What you're doing from the fundamental theorem of calculus, I think it's part 2, what you do is rewrite this as the integral from, and do they put, yeah, since your initial value is x equal 3, they'll do 3 to x e to the minus t squared dt. Remember when they did that mess on you? as long as this is some a down here, which we're going to use that one, and then they're being sort of sloppy about it here. But here's what they're doing. Now, like I say, this is a little sloppy. They're writing this also as a dy dt dt. That is a dy. Now, over here the t is going from 3 to x. So over here they let t go from 3 to x. Okay. Now this almost seems like a shell game. They're just messing around with changing the variables. So they changed this variable. This is a dx and the x squared. And they moved the variable x to up here. This is, like I said, fundamental theorem of calculus part 2. And made t the dummy variable here and went from there. This is indeed the same as that. So what they had to do was get something here to be like that. So they changed this to dy dt dt, which is just a dy, but then this enables, since t is going from 3 to x, enables you to go from 3 to x here too. And again, there's no dy dt anywhere in the problem here, but yeah, it's just a dummy variable. That's e to the minus t squared. But that's all on the right-hand side. Over here, the antiderivative of this is just y, but it's y evaluated at x minus y evaluated at 3. Right? Since you put limits on it here, which you had to do to deal with your undefined non-integrable integral, okay, rewrite it in terms of fundamental theorem of calculus part 2, rewrite it that way. Well, when you did that, you needed to rewrite this one that way, and this gave you y of x minus y of 3. And this you still can't do anything with. This is the integral 3 to x e to the minus t squared dt. You can't solve that any easier than you could with the x squared in there. So you just leave it like that. Okay? Now, what you can do here is add y of 3 to both sides. But y of 3 is equal to 5. So this goes to 0. So you got your answer, y of x. That's what you're looking for. What is y? Y of x is equal to 5 plus this integral defined answer, 3 to x e to the minus t squared dt. Now that's not very satisfying, perhaps. But I want to point out to you what this is. Have any of you ever asked an instructor or professor, do you grade on the curve? Or have you heard anyone ever ask that? Yeah. Okay. This is almost the curve. When you graph this, it's symmetric about x. When x equals 0, this is 1. Or t is equal to 0, that's 1. And then it goes down like this. Basically, that's where you say you're related to the normal distribution. Okay? It's not exactly, because they have some different coefficients out in front, but that's exactly what it is. They have tables for things like this. Or you do a numerical integration with it. Something, other techniques than what we have in this book, it can be solved. Add 5 to it and get done. Okay? For any value x, you can come up with a value y. Not particularly satisfying, okay? But that's what you do. This is what they call an integral defined function. When you get an integral you cannot integrate, then leave that as your function, and this is the technique for doing it. And again, it sure doesn't feel very satisfactory. It doesn't feel like you've done anything, but it's all you can do. Okay? So there is your answer, y of x equal 5 plus whatever integral that is. But as you can go to tables or numerical integration packages or whatever and find that out. Now, there is a single remark here, and if my memory's right, I got almost absolutely nothing out of reading this remark. It seemed to be repeating some of the same type stuff we had done before, but it's leading on into what's coming next. So anyway, if I hadn't told you before, the homework exercises here, any of the odds that are in the back of the book, 1 through 21, try those. The odd number problems are found back in the back of the book. Any of the odds 23 to 27 that are in the back of the book. Number 29 if it's in the back of the book. 30 or 33 if they're in the back. 35 or 37 if they're in the back. 39 or 41 if they're in the back. 43 if it's in the back. And any of the odds 45 to 49. I bet you those are... No, I thought those were integral defined functions, but looks like they may be solvable. All right, most of the time the discussion problems are not in the back. The answers are those are not in the back. If any of them are, you might want to look at those just to see if you can follow what they're doing. There's a mathematical model problem that's catenary. I think it has a different name. But you can look at that if you like. And then there's some computer lab assignments. I don't have a computer lab we can work with. If you do have one, access to one, you can knock yourself out on those. 2.3 then is moving to what we call linear equations. And again, chapter 1, as you saw by the test, is verifying that this is a solution for that and those kinds of things. Chapter 2 is actually solving. And so here we'll do a new kind of problem called a linear equation. These are not necessarily, in fact, usually not separable. If they are separable, separate them, okay? That's the easiest way to go. But if they're not separable and they fit the pattern here, then here's a new technique you can use. Or as like I said, my professor that I had, I was very, very fortunate to have the same professor for all 5. We were on the quarter system back then, all 5 quarters of calculus. Okay? Same professor. He was excellent. Hard as nails, but he explained things so incredibly well that even though I didn't know beans about what he was talking about in the beginning, when I go back and look at the end of the term and look at his notes, even as lousy as I took notes, they made almost perfect sense. And so I usually was able to figure out what in the world he'd been talking about all term by the end of the term. Now, occasionally I could follow him for a while there, but he was really good. And we actually finished Cal 5 with about a week or two to spare. We had calculus 5 days a week, Monday through Friday. I can't remember what time I had. I think 10 to 10:50. 50-minute classes, 5 days a week. And we finished everything in Cal 5. He said, well, let me get you ready for differential equations. So he started and told us. And here was the thing he said. He said, differential equations basically is developing a trick. And if the trick worked more than once, call it a method. And that's what he said it is. They just found ways that work, tricks that seem to work, and when they work, call it a method. Okay? And that's what linear equations do. Separable, you just separate them. You know, that is pretty straightforward. And then integrate both sides. Linear equations, you got a little more work to do. Try a trick. And if and when it works, call it a method. So here's, we continue our quest for solutions for first-order differential equations by examining linear equations. Linear differential equations are an especially friendly family, of differential equations in that, given a linear equation, whether the first order or higher order, there always is a good possibility we can find some sort of solution of the equation that we examine. So here's the definition. The form of a linear first-order differential equation was first given back as equation 7 in section 1.1. That form, in the case where n is equal to 1 in example 6 of that section, is reproduced here. So here is the definition again. A first-order differential equation, I'm just going to put DE, differential equation, of the form a sub 1 of x dy dx plus a sub 0 of x times y is equal to some g of x. Okay? Is said to be a linear equation. I'm going to put DE, differential equation, in the variable y. Okay. Now, let's go back and remind ourselves what we meant by linear. Okay? Anytime you see a y or a y prime or any higher order different derivative of y, they must be isolated. They must be no otherwise. You couldn't have, see, this is a coefficient function of x. You can have any function of x here as long as there's no y in it. If there was a y times a dy, that's not linear. Or if there's a, again, this can be any function of x. It can't have any y's in it. This y can only be first power linear, right? No y squareds, no y to the 1/2, no y to the 0.3, no y to anything, no 1 over y's. That won't work. It has to be linear. First order, it's a first derivative to the first order power with no cross term, no other y's here. Y to the first power, linear, no other y's in here. On the right hand side, just functions of x. Okay? Now, as you might imagine, with the plus sign here, it's going to be very difficult to separate variables here. Very difficult, okay? Because you can't have any y's here, you can't have any y's here or here. You have a y here, but that's not going to be separable because you can't factor them out. And then with the a of x and g of x, hey, the likelihood of those being separable really, really important. Okay? So this is going to be a linear function. Anything that looks like this, I want to say anything, usually is solvable. Maybe not always, but usually. Okay? I mean, you can have some really weird a of x's or g of x that may not be solvable, but let's see. Okay. Now, that's not quite what we call standard form yet. Here's what we call the standard form. If you take this and divide by a1 of x, divide by a1 of x, divide by a1 of x, okay? Now these go out and you have dy dx is now some other function of x only. Remember, a of x is only a function of x, a1 of x is only a function of x. So this is still a function of x alone. You didn't introduce any y's, there's no y's in it, so this is still a function of x. Well, I'm not going to call it a0 over a1. I'm going to give it a new name. Fred, no, p of x plus p of x times y is equal, now let's give that a new name too. Let's call that one f of x. Because it's just a function of x. It's g of x divided by a1 of x. Could be all messy and but it's all messy and x's alone. No y's in them. This is now our standard form for our first order linear differential equation. Okay? If you had a coefficient here, even if it had no x's in it, 7, divide by 7. It's still fine. Have this with just a dy dx. This is only a function of x. Y is to the first power only, no cross terms, no other powers of y. And this is some function of x alone. It can be ugly, messy, but that is a linear equation in y. Okay. Now, what you're doing is looking for a solution for that. But it says, before we examine a general procedure for solving equations of that form, we note that in some instances, this can be solved by separation of variables. I said in general it can't, but occasionally it can. Okay, here is one sample that could be. dy dx plus 2xy is equal to 0. Hey, this is linear. P of x is 2x, y is y, and f of x is 0. That's a linear function in y, but it easily can be solved because of that 0 there. Subtract this from both sides, and then divide by y and multiply by x. That's simple. That's the way to go if you can do it. So you don't have to use this technique on ones that are not simple. I think when they first show it to us, they're going to have us do some that are separable, and then show us that we did get the right answer. We're going to use the linear technique, which is usually a little bit longer, more involved, but it's okay. Then we'll do it separation so you get the right answers, the same answers. Okay? So that's what we're going with. Now here's another one. Okay? dy dx is equal to y plus 5. Now, wait, that's not in our standard form. I wish they'd have given it in standard form first. Standard form could have been dy dx minus y is equal to 5. Now that's in standard form. Your dy dx is right like it's supposed to be. Your p of x is a minus 1 times y is equal to f of x plus 5. That's in standard form. But this is easy to get to this form. And then that's separable. Divide with this, multiply with that. So that's another one. You don't have to have a 0 over here. There are other ways it can be separable. That's one. Okay? In fact, in this form, anytime that's a constant, you can easily separate. Maybe not easily. If that's a constant, and this is a number along, a constant 2. No. If that's a constant, I don't want to make up any rules. I can't prove every one of them works. Okay, but both of those are linear, but they are separable. How about this one? dy dx plus y is equal to x. That's certainly linear. dy dx, that's fine. The p of x is just 1. Times y, f of x is x. Fine. Any way you can separate that one? Try like you might, you can. Because if you subtract y from both sides, you get x minus y. If that was x times y, that would be fine. But x minus y, you can't separate. So this is one that you can do. Just looks no more complicated than these two, not separate. So this one you have to use the technique we're going to develop. We haven't gotten there yet, but we'll get it. Now, they can manage to take something fairly simple and muck it up so badly you don't think it's simple anymore. But let's try following this and it will work. Okay? Now, here's what we're going to start with. The method for solving our linear form, I'll write it down again. dy dx is equal, plus p of xy is equal to f of x. That's our standard linear form. Dy dx is by itself. P of x is just some function of x. It could even be a constant, but that's fine. So some function of x. Y is to the first power and nothing other than the first power. F of x is some other function of x. Okay? That's what we're starting with. So the method for solving that hinges on the remarkable fact that the left-hand side of the equation can be recast in the form of an exact derivative of the product by multiplying both sides by some function mu of x. Okay? So here's what they're going to do. They're going to start with this. And again, they can make something fairly simple seem pretty complicated. Here's what they're going to do. D by dx of a product. This product is some unknown mu of x times y. Okay? Now, can you tell me by the product rule what that turns out being? By the product rule. It's a mu, yeah. You want to start with that? Mu of x times dy dx of y prime. That would be fine. You want to write it that way, that's fine. That'd be a little neater. Okay, plus y times mu prime of x. Okay? Yeah, you're absolutely right. Okay. Now, if you can do this, have this form right here, that's mu times the left-hand side, right? Or the first term on the left-hand side. Okay? If the y times d mu dx, okay, this is going to look strange, but hang with me. Because like I said, they could dy dx plus u p y. Okay. Now, what they are doing, they're multiplying this by mu, and this by mu. Okay? Same function, right? We just multiplied everything by mu of x. Okay. Now, this term right here is exactly that term. If we could get this mu prime to be this, then that would be the same thing as this. If mu times p would be mu prime. that would be make our day. Okay? So that's what we're aiming for. We want d, this is d mu dx to equal mu times p of x. Okay? Mu p. That's what we want to happen. Now, that's a separable differential equation, isn't it? Okay? So let's separate it and make it d mu over mu is equal to, and remember this is a p of x dx. Right? What is the, let's integrate both sides of that. And what do we get? Natural log of mu is equal to integral of p of x dx. Okay? Now, how do you solve that for mu? How do you undo a log? Yeah, we'll do an e of both sides, and that e of log x would be e of this. E of log mu would be that. So mu would be equal to e to the integral of p of x dx. If you choose that to be your mu, you can make that thing up there happen. And if you can make that thing up there happen, you've got it solved. Believe it or not, you do. Okay? So this is called the integrating factor. That is called the integrating factor. Okay? Mu of x is equal to e to the integral of p of x dx. All right. Now, from this stage on, they have murked it up a little bit, but not so awfully bad. Okay? The next bit of stuff that they do really makes it look complicated. Okay? And I guess I'll do it just because they did it too. But actually, let's just leave it right there. I'm going to see if skipping all that part will work for us. Okay? Maybe not, but that's our integrating factor. So let me erase all this, and here's what we're going to do. Remember, this is solving a linear first order equation. Remember to put the linear equation in the standard form. If you got other variables in there, get it in the standard form, which is dy dx plus p of x y is equal to some f of x. No matter how complicated that p and f are, get it into those forms. Okay? Then once you do that, the next thing you do, I'm going to break it into smaller steps. Integrate p of x dx. Do that first. Okay? When you do that, don't do a plus c. Don't worry about constants. Just do that. Once you got what that is, hopefully it's an integrable function. If it is, you're in good shape. Then once you get that, raise that to the e power as the e to that function. That then is your integrating factor. Okay? Now, you multiply everything on both sides of the equation by that. Okay? Now, that's what they did up above, and it really clouded the issue really badly. Multiply by that. Okay? And that's what I just said. Okay? Once you've got that done, then hopefully you will see that you have, and this is where the magic happens, you'll see the left-hand side is a perfect derivative, and it's really easy to integrate, okay? So at that point, just integrate both sides. Now, that's a lot of blah, blah, blah. Let's actually do it. I'm going to erase this. Now, here's a linear equation, a very simple dy dx minus 3y is equal to 0. Before anyone starts yelling or shouting or anything, yes, that's simple. We could do it much easier than this, but we're going to do this on a simple one that we can show gives the same result. And we'll come back and do it as a separable. But let's do it now. Okay? Now, first, is it in standard form? dy dx is by itself, so it's perfectly fine. You got a y there, so your p of x is minus 3. And your f of x is 0. Okay, so yes, that's in standard form. So identify your p of x. P of x is equal to minus 3. And then what do we do with that p of x? We integrate it. I'm going to leave the minus 3 on the outside because it's not going to affect the integration at all. And what does that give us? The integral of p of x dx is equal to minus 3. What's the integral of dx? X minus 3x. There's your integral. Okay? What do you do with that? Raise it to the nth power. There's your multiplying factor, your integrating factor. Okay? E to the minus 3x. All right. What we do is go back to our original equation and multiply this by everything on both sides. Okay, time out. Is that ever 0? E to the minus 3x. E to the nothing is ever 0. E graphs like this. It's never equal to 0. It gets close to 0, but never gets there. It can be down here or down here, but it's never 0. E to the minus 3x is never 0. So it's okay to multiply everything on both sides. You never multiply by 0, okay? And this isn't 0, so you're okay to do that. Okay? So we're going to come up here and do e to the minus 3x dy dx minus e to the minus 3x times y is equal to 0. Agreed? Because e to the minus 3x times 0 is still 0. Right? Now here's the point where you take a look at this and say, is this a perfect derivative? And basically what you're doing is using the product rule, right? Is this perfect derivative of e to the minus 3x times y? That's the question. Is it? Let's do the product rule on it and see. We got stuff. No, I think we're okay. Yeah, I did leave out. I left out something. I left off my 3. That's what was throwing me. Because it's minus 3y times, see, I was multiplying this thing by everything here. I left off the minus 3. You see, this thing times that is that. And what I did was minus, I just put this times y. I forgot the minus 3. So when I multiply this times that, I get minus 3 e to the minus 3x. Because when I looked at this, I said, no, that's not a perfect derivative. Now is that a perfect derivative? Let's take the derivative of this and see. Take the derivative of the first one. Product rule. E to the minus 3x. Wait, where'd you get a y squared? You're not integrating, you're taking a derivative. It's times dy dx, isn't it? This times derivative of that would be that, right? Is that what you were doing?
I'm not following.
Okay. All right. Slow down. Start back. Okay. Here we got a product rule. Right? We're taking derivative of a product. Right? Okay. This times that. So how do you do a product rule? First time derivative of the second. Is that how you start? Okay, so let's start it that way. The first, which is that, e to the minus 3x times derivative of the second is dy dx. Yay or nay? Right. Plus the second, y, times derivative of the first. What's the derivative of the first? What's the derivative of e to the minus 3x? Okay, it certainly has e to the minus 3x in it. Yep, e to the minus 3x. What else? Chain rule. Times a negative 3. So I'm going to lose the plus sign, make it a minus sign, and then put a 3 here. And what do we have? We have precisely that. All right, I've got my y here, so that. We have precisely the same thing, right? Yay? Okay. So if this is a perfect derivative, okay, that thing up there is a perfect derivative, what we can do is then write it this way, and this is equal to 0, by the way. Okay? Then we can say d of this part, e to the minus 3xy, is equal to 0 dx, okay? And we're going to integrate both sides of that. Well, the integral of a perfect derivative, this is the fundamental of theorem of calculus part 1, I believe, is just this, e to the minus 3xy. And what's the antiderivative of 0? A constant, right? Just some constant. Okay? And then this implies multiply both sides by e to the 3x, and that gives you 1, right? So here's our solution. Y is equal to c e to the 3x. Right? Okay, magic, huh? Let's see what happened if we separated variables. dy dx is equal to 3y. I just added 3y to both sides, right? I'm going back to the original problem. Now divide by 3y, or divide by y, and why don't we have dy over y is equal to 3 dx. Is that okay? Yay or nay? Okay? Then integrate both sides of that, and what does that give you? Anti-root of dy over y. Natural log of y is equal to 3x, and you could put in a plus c if you wanted to, right? Okay? Now, what do you think we could do with that? Yeah. Do an e of both sides. This will be y is equal to e to the 3x times e to the c. Can't you do that? And e to the c is just some constant, so call it y is equal to c e to the 3x. Way easier to do it. Separation of variables, you get the same answer. So this technique worked on that one. Okay? So y is equal to e to the 3x. And by the way, whenever you have a solution, you should give an interval that's good from minus infinity less than x less than positive infinity. I started to put an equal sign, but infinity is not a number, so you can't have an equal sign there. That's for all real numbers, x. No problem anywhere. Okay? That worked, didn't it? Need it a little longer? Okay. This step here, anytime you had a base to a sum, that's the product of the bases. Okay, so that's where we got. Went from here to there, and then since this is a constant, it's not the same c. We could have called that c1 and that c1, so this would be a new c. But it's just a constant. E to the c is just a constant. Call it anything you want to. I call it c. Okay. Ready for, I'll let you finish writing. That was example 1. Everybody got it? Finished? Okay. Then, let's do example 2. dy dx minus 3y is equal to 6. Now this looks awfully much like the last one, except you got a 6 there, not a 0. Guess what? This is also separable. Not going to do it separable till later, but it is separable. And how would it, okay, if you're going to try, is it a linear function? dy dx is to the first power, no other y's involved with that. Your y is to the first power, no other y's or derivatives of y associated with that. And your coefficient of that is not got any y's in it, so it's a function of x, even though it's a constant. And your right-hand side, a function of x, even though it's just a constant. So yeah, that's good. And is it in standard form? Yes, it is. What's the first thing to identify? P of x is equal to negative 3. And then what's the next thing we do? We integrate that dx, and we integrate this dx. And what does that give us? Negative 3x, just like before. Don't ever put a plus c in this one. Not yet. We'll come to something later. So what do we do with that then? Yeah. You raise it to the e. I mean, raise e to that power. You do e to the that, e to the px. That's what you're wanting to do. That becomes your integrating factor, e to the minus 3x. Okay? And then what do? Since that's the integrating factor, you multiply it by every term on both sides. So this gives you e to the minus 3x times dy dx minus 3. I remembered the 3 this time. Y e to the minus 3x is equal to 6 e to the minus 3x. We didn't have that before. Okay. Now, this is exactly what we had before, and this is a perfect derivative, isn't it? It's a perfect derivative of the integrating factor e to the minus 3x times y. Don't believe me, do it. Okay? It'd be this times this, dy dx, that's it, plus y, there it is, times the derivative of this, which is minus 3 e to the minus 3x. So yeah, it's a perfect derivative. Okay? And that's equal to 6 e to the minus 3x. So what we do with this is write this in differential form, put my dx over here, and integrate. Okay? Well, the integral of a perfect derivative is e to the minus 3xy, right? Integral of a derivative, perfect derivative, is that thing inside the derivative. Fundamental Theorem of Calculus, Part 1. Over here, what do we have? Negative. Okay. We're integrating this, not differentiating. It will be negative, but integral of an e is itself, right? So you got to... Okay, I'm going to leave off the negative for now. We'll come back for it. Okay, let's just do it a step at a time here. You got a 6 out front. And the antiderivative of e to the minus 3x would be e to the minus 3x. And now you unchain rule it, which is dividing by the negative 3. So that's where the minus came from, and you divide by 3, right? Now, if you don't believe it, check it, okay? This will be a minus 2 e to the minus 3x. Take a derivative of that, and what you get? Minus 2 e to the minus 3x times a minus 3, which is 6 e to the minus 3x, right? Yeah, so that does work. All right? So here's what we got. Now what we want to do is, again, multiply both sides by e to the plus 3x, right? Or you could divide by e to the minus 3x if you prefer doing that. Would that be better? You want to get this to the other side, right? So which you want to do? Multiply by e to the 3x or divide by e to the minus 3x? It's the same. Multiply? Okay, you're okay with that? So multiply this by e to the 3x. Okay? What does this give you? These multiply to be 1, right? E to the 0 is 1. So that would be y is equal to, you let me get away with it. There's supposed to be a plus x in here, so a plus c in here somewhere, isn't there? When you did that integral, plus c, and let's do a plus c here before we multiply by that. Okay. I'm sorry, this is ugly now, but it's e to the 3x times minus 2e, that's just going to give you a minus 2, right? Plus c e to the 3x. Right? If you multiply both sides by e to the 3x, you have two terms here. First this term, which is just a minus 2, and then that term gives you a c e to the 3x. Okay. Whoa, is that our answer? Oh, there it is. Minus 2 plus c e to the 3x. And again, that's good from minus infinity. Okay, all real numbers x. All right. Remember we said this was separable? Want to try it separation? dy dx is equal to, you want to do 3y plus 6 or 6 plus 3y? Does it matter? How about 3y plus 6? Is that right? Just added 3y to both sides. Okay? Or, let me actually write it this way, 3 times y plus 2. Is that okay too? Okay. So let's write it that way.
Yeah, that is better.
Okay. Okay. Now, let's divide by the y plus 2 and multiply by dx. You have dy over y plus 2 is equal to 3 dx. Yay? Can we integrate the left? Now, we probably really should put absolute values on it, but okay. Is equal to 3x plus c. Now, I'll probably want to change what that c is, but whatever you want to call it, c1, whatever. And then what would we do? E both sides. Okay, and when you e this, you get y plus 2, right? And when you e this, you get e to the 3x times some e to the c, which is some constant. Let's just call that a c1. This will be a c, right? So this will then be y plus 2 is equal to c e to the 3x. Subtract 2 from both sides. And you've got the same answer you did there. Right? Yep, it worked again. So sure enough, that will do it. So y is equal to minus 2 plus c e to the 3x, good from any value. Now, how does this one look? They didn't show the first one, but they do show this one. When y is equal to minus 2, that's your equilibrium position. Because actually what you have here was especially when I wrote it that second way, it was a autonomous equation. dy dx is equal to 3 times x minus 2. No, x plus 2. Remember? So y is equal to x. Y is equal to minus 2 was the equilibrium position. So that's going to be, for your various values for c, then you take on one of these lines here. Why they have some dark colored on top and light colored on bottom, I guess is plus or minus, I don't know. But that's your equilibrium position. Okay. All right. Now, as soon as everything is running smoothly like it was, they usually throw something else in. And here they're throwing in this concept of general solution. Suppose again that the functions p and f in that original equation, like this, are continuous on a common interval I, and the steps leading up to your answer, we showed that if 2 has a solution on I, then it must be of the form given in our solution. Conversely, it's a straightforward exercise to differentiation to satisfy that the function of the form given in the final is a solution of the differential equation initially. They're doing equation 3 of 2, equation 4, blah, blah, blah. In other words, 4 is one parameter family of solutions for equation 2. And every solution in 2, defined on I, is a member of that family. Therefore, we call the 4, this thing like we just wrote here, a general solution of the differential equation on the interval. Okay? They want you to go back to the remarks at the end of section 1.1, which they gave you long before you were able to visualize what they're talking about. Maybe you can now. I found those remarks boggling. If not mind-boggling, they just boggle. Okay. Now, by writing 2 in the normal form, y prime is equal to some function of x and y, we can identify f of xy as minus p of x, y plus f of x, little f of x. Goodness gracious, what are they doing here? From the continuity of p and little f on the interval, we see the f and partial of f with respect to y are minus p of x from the continuity. Goodness gracious. They're also continuous with the they did all that talking just to get down to the place of saying, so if you have a linear differential equation, dy dx equal p of x, y times f of x, equal f of x. If you have that with an initial condition, y of x0 is equal y0, yeah, then it works. Well, we've already been saying that with an initial condition, you can find out what the c is. So, I don't know. All that blah blah at the end there didn't say anything new from what we had before. Do we have time to do example 3? Maybe, maybe not. You want to give it a shot? X times dy dx minus 4y is equal to x to the 6th e to the x. My question for you is that a linear differential equation? Yes, it is. The x is just some function of x. dy dx is not multiplied by any other y or raised to any power, so that's fine. Minus 4 is just some function of x, not even a function of x, but it could be written as that. Y is written with no y's and with no y primes or anything else multiplied by it, so that's to the first power, that's fine. The right-hand side, as ugly and messy as it is just some function of x. So that is a linear. Is it in standard form? No, the x keeps it from being in standard form. How do you get it into standard form then? Divide everything by x. So we know right now that x cannot equal 0. Now, I don't know if x equals 0 is going to do anything to begin with, but at this point you know it can't be because we're dividing by 0. Of course, if x were 0, then we would have minus 4y is equal to 0 and y is equal to 0. That would be a singular point 0, 0. And that's all, folks. So that's not much of a solution, but that's not going to be a case now. Okay, so x can't be 0. So we divide that by 0, that by x, this by x, and this by x. Okay? So now what's our equation? dy dx over x, y is equal to x to the 5th e to the x. There we have it. Is this in standard form? Yes, it is.
Why didn't we divide y by x?
We could have, but I want to divide that 4 by. Because you see, I want this to be my p of x. I want to leave that y alone by itself, naked y.
Like, I get that.
Right.
I thought you had to.
Well, you can't divide both of them by y, x. So since I want this to be a function of x and that not to be, I want y by itself. Just like I didn't divide this by x either. I wanted to divide that by x to get rid of it. I wanted to divide this by x to keep that a function of x. And then I could have divided it here, but it just made more sense to divide it by x. You only divide by x once, some factor. So those are the factors I chose. So is that in standard form? Yes. dy dx is by itself. There's a function of x times y and a function of x. You're happy. What's the next thing we identify? What is your p of x? So what is your p of x? Minus 4 over x. And what do we do with that? That's a 4. It's ugly 4, but okay. What do we do with that p of x? Okay, you integrate it, dx, so you integrate this, dx. Okay? So this integration of p of x dx is going to be, like I heard Bill say, minus the natural log, minus 4 times the natural log of x. Isn't that what you said? Don't put a plus c on it. Do not put a plus c here. Okay? Now, what's the next thing we're going to do with that? We're going to exponentiate it, but before we do that, let's get a pure log. So let's write that as log x to the minus 4 power, right? Rule of logarithms, okay? If you have a coefficient out in front, make that the exponent of the argument, right? Now let's e it, okay? We'll e that and e this, okay? And what does that become? X to the minus 4. That is your integrating factor. Remember, e to the p of x, that's your integrating factor. That's our e to the minus 4. X to the minus 4. So, that's what we multiply. So let's go back up here. I'm going to erase this, but don't let me forget it, because I need this room over here. But don't let me get it. X can't be 0. In fact, I'll write it here. X cannot equal 0. Okay, remember that. Okay. Not that we'll necessarily use it, but just remember. So let's multiply everything up here. Oh, it's the form I wanted to anyway. Who cares? This is what I want to multiply by integrating factor. X to the minus 4 dy dx minus 4 over x to the 5th, right? Because x to the minus 4 is 1 over x to the 4th, right? Isn't that the same thing? Multiply that by that and you get minus 4 x to the minus 5 times y is equal to, and when I multiply x to the minus 4 times x to the 5th, that's going to be x e to the x. Yay or nay? Got it? Everybody agree? Okay. Now, the question is that left-hand side a perfect derivative? If it is, it should be the perfect derivative of your integrating factor which would be x to the minus 4 times y? That's the question. Is that a perfect derivative? Let's do the product rule and see. It's this right here times the derivative of that. That part's good, right? And then it's this, there it is, times the derivative of this. And what is the derivative of that? Derivative of this. Derivative of x to the minus 4. Minus 4 times
X to the negative 5 or 5 to the negative.
Yeah. So is that it? Yes, so that is a perfect derivative. Okay. Whoa. And that's equal to x e to the x. So what are we going to do with that perfect derivative? Write it as a differential, integrate both sides, and what do we get? This just gives you x to the minus 4 times y is equal to, SpaghettiOs. Can we do that? Integral? This integral right here. Yeah. Integration by parts. Parts is parts. Okay. How does that work? Let u equal x and dv equal e to the x dx. Okay. Why I chose that? When you differentiate this, it gets simpler. When you integrate that, it doesn't get any worse.
Well, if you do it the other way,
Then you wind up with an x.
You'll figure it out
It
eventually.
gets worse. Okay. So that's why we chose it that way. And then that's what we do. Then du is equal to, that's a u, it's an ugly u, Bob, dx, and v is equal to e to the x. Okay. And then what does this give you? Your u times v, which is x e to the x, right? Minus the bottom line, the integral of e to the x dx. And what is that? That's e to the x. So I'm just going to wipe that out, minus e to the x. So here's what we got. X to the minus 4th y is equal to x e to the x minus e to the x. Oh, somewhere here I was supposed to put a plus c, wasn't I? At the end. So we'll do a plus c out there. So this is going to be a plus c. All right, and what do we do next? If we can, write your answer explicitly in terms of your y. I mean, in terms of x. Y is a function of x. So what do we do? X to the 4th, right? This will be times x to the 4th. We'll make it x to the 5th. This will have an x to the 4th here, and this will have a x to the 4th here. Okay? So we have y is equal to x to the 5th e to the x minus, see, is there going to be any way to make this any better? I wondered if we wrote that as an e to the c, would that do any better? If we wrote that as an e to the c. e to the c, and that would be x to the fourth times e to the x minus c. Is that any better? I don't know. We're running out of time. In fact, we're out of time.
It doesn't matter at the end of the day, right?
It really doesn't.
C.
See, which one are we doing? Oh, there it is. There it is. Okay. No, they left it as the way I did the first time. They left it just like this. Y is equal to this thing here. X to the fifth, e to the x, minus x to the fourth, e to the x, plus c, x to the fourth. Yeah. Not that. Okay. It wouldn't make any difference. Okay. Now, remember, it can't equal 0, obviously, because then y is equal to 0 would be your only solution. Then that would be a singular point in the equation, because that could be a solution, because when x equals 0, y is equal to 0. But, except for that, this would work. Okay. All right, one parameter system. So we'll begin the next time at example 4. Homework exercises here. You can do any of the odds 1 through 23 that are in the back. Well, that we've done so far. Some of those we may not have done somewhere. Any of the ones like the ones we've done in there. I can see 1 through 7 for sure. 9. Excuse me. At least through 11. You might be able to do more than that. If you can, do as many as you can. But if you run into any real nasty ones, stop and we'll see if we'll pick up some of those later. No, we didn't get to initial value problems. All right, good deal. On this, answer is only good for x is greater than 0. We know it can't be negative, and I don't know. Don't want to mess with it too much. Can't be 0. Maybe negative x would work too, but it can't be 0. I know that much. They say 0 to infinity. All right, we'll leave it at that. Pick up with example 4 next time. Good deal, folks. Sorry if I ran over a little bit.